Hello, welcome everyone to this webinar. I'm going to talk about addressing exascale emulation debug complexity, the case for a system level approach. My name is Ribhu Mittal and I'm Director of Emulation Application Engineering. So the agenda for today's webinar is going to be, I'm going to describe what exascale debug challenge is, what are the key issues with the current debug solutions, and then once I have laid down the requirements, I'll get into the ZeBu specific solutions and how we are addressing exascale debug complexity. Towards the end of the webinar, I'll share some of the case studies to showcase the value of ZeBu debug, and then we'll do Q&A at the very end. So if you can please hold off to your questions, that will be helpful. So let's get into exascale debug. Now, when we are talking about the debug complexity, there are two main factors. First is how big your design is. That is the number of gates in the design. The bigger the design, the harder it is to find one gate that is misbehaving. And the second big factor is the number of cycles or how long the test case is, because eventually your goal is to find one cycle where things start to go wrong. And if you look at IP and subsystem type of designs, these really fit into this bottom left corner because these are less than a billion gate, and the test cases that are being run here are usually lesser than a billion cycles. Now, from here, if you think of the increasing complexity, and this is where I want to get into exascale, which is 10 to the power 18, and in terms of debug field, I want to define it as a billion or more gate design running billion or more cycle test cases. And now that you have this area of exascale debug complexity, pretty much all of the verticals that we have in modern SoC designs, starting from mobile to server CPUs to GPUs to networking to AI, all of these design verticals actually fall within this exascale debug complexity space. So now, when we are trying to debug an issue on these different designs, if you look at IP and subsystem, we have predominantly done waveform-level debug. Now, from here, when you go to SoC level, that is running some software contents, the premise I'm making is that we need to raise debug abstraction, and I'm calling here system-level debug, and we'll get to it in the webinar. And then finally, there is another higher level on top of that where you are trying to do application level debug of the SoC in system context. So clearly our complexity is increasing from millions of cycles and millions of gate design to billion of cycles being run on billions of gate design. In today's webinar, the focus is going to be on system level debug and waveform level debug, and in a future webinar, we will talk about application level. So now let's look at a real world example of this exascale debug challenge. And this is something that we've seen in several of our customers, and take the case of simple bring up that you're doing OS boot and then you're running some applications. In this case, we have a Windows boot followed by some system services, and then finally user is doing some application which is based on internet browser. And while running this application, after running the test case for a few billions of cycles, they eventually hit a failure, and let's say that the failure is observed as a OS hang. Now, the root cause of this failure could be several billion cycles before, and let's say in this case it is a cache coherency error that happened during the boot, OS boot itself, which we finally caught it billions of cycles later. So now, as you can see that if you're doing traditional waveform level debug and the typical sample length is 1 to 2 million cycles, you can imagine how many iterations would you require to cover entire 2 billion space and get from failure to the root cause. So this is the real problem that we've seen, where the time to root cause becomes very long and unpredictable with iterative waveform level debug. So let's look at this problem from a totally different angle. And as I was describing that in the previous slide, that we are trying to debug a problem in exascale space, which is pretty much like a search space problem, and you're trying to identify something within the search space, and so graph theory becomes a very good parallel to review the debug strategies. And from graph theory concepts, the iterative waveform level debug is very much similar to depth first search, where you're starting from the root and then you're going in depth, trying to find to a root node, doing full in-depth analysis of that node, right? So in terms of debug, essentially this is your 1 to 2 million cycle window that you think is where the root cause is, and then you're doing full waveform based debug to check if the root cause is truly here. Now, if that is not the case, then you traverse the graph, you get to another window of interest or another node in the graph, and then you do the full analysis there. And then you continue to repeat these until you actually found the window where the root cause is. So this actually works out very well for IP and subsystem designs that are smaller in size. But when you get to a bigger design, which is represented by a large graph here, the number of iterations to find the problem becomes one too many. And this is really the problem, that essentially your time to root cause is going to increase exponentially if you completely depend or solely depend on iterative waveform level debug. So now to debug this problem, clearly you need to get to a higher level of debug abstraction and find a flow that can address this problem. So that is really the first challenge with exascale debug, that iterative waveform level debug is not enough. Now let's look at another problem that we face often when we are trying to do exascale debug. So traditionally, here I have an example of low throughput emulation, where the DUT clocks are stopping. So DUT is actually running only when the test bench is not running, as shown with the thick line here. And on top of that, because of the DUT start-stop, there is going to be some latency built into it. So, with this type of a low throughput emulation, your overall throughput of the test case can be impacted by up to 5x. On the other hand, if you look at a high throughput emulation, DUT clock never stops. It is always running, and then we are able to speed up the throughput by parallelizing test bench and DUT execution. So with those concepts, now let's look at a typical emulation where you have multiple test bench interfaces. So an example could be that you have a DUT, there is a PCI interface, there is USB interface, and all of these asynchronous interfaces are working together and trying to send some instructions to DOT to execute. Now, you may hit a failure that is coming because of the specific timing when these test bench instructions are coming inside the DUT. So this is what you saw in regression. Now, when you wanted to do the debug and you wanted to reproduce the problem to find the root cause, because test bench is now running parallel to DOT depending on the system load, etc., the timing of test bench instructions can change, and they can arrive in DOT at different time, and as a result, you may not see the failure that you saw in the first run. So you did another run, and it so happens that the timing got changed again, and you still did not see the original failure. And this can continue through several iterations before you're able to reproduce the failure that was seen in regression run, and you're able to debug the problem. So this is really important, that for exascale debug, you need high throughput emulation because you're trying to run billion cycles. So and when you have set up high throughput emulation, deterministic bug reproduction becomes a very, very important debug requirement for such a system. Now let's talk about the third challenge. So here I'm talking about waveform-level debug to do the final level analysis where you're trying to find exactly the root cause. And in case of the flow is that the design is running on emulator. We are doing raw data dump, which could be just the sequential nodes of the design, and then you're doing some expansion of the waveform to generate full visibility waveform that is represented as expanded debug data here, which is then get loaded into the waveform debugger that you have. Now, in case of a small design running small test cases, the data that you get is megabytes, the raw data coming out of emulation. It takes a few minutes to expand, and then the expanded waveform, full visibility waveform, is closer to a GB, usually less than a gigabit, and then it takes a minute or so to load the waveform in the debugger. So this is very efficient process. Now let's scale that up to SoC and software emulation, where you have exascale type of a debug scenario. You're doing the same flow. However, the amount of data that is being generated is a magnitude higher here. So the raw data is now gigabytes. The expansion time is several minutes, and it gets into hours. And then the full visibility waveform is multiple GBs. And because this is such a huge design, it can take several minutes, which are closer to the hour limit, to load such a big design into your debugger. So now you can see that all of this process is going to put pressure. It is going to get slower, and it is going to increase your time to root cause. So really, the third challenge is that, or the third issue where that exascale debug really brings up is that we need engines that can expand the waveform fast, and we need engines that can load the waveform fast into the waveform viewer to reduce time to root cause. So now that we have listed the three challenges, let's quickly look at the three requirements. What is needed to solve those three challenges? So the first challenge was, how do we reduce time to root cause by eliminating iterative waveform level debug? And here, again, going back to the graph theory, the requirement is that we need to do a very higher level analysis of the entire design over the entire billion cycle run. So in terms of graph theory, what we want to do is something called breadth first search, where you're trying to evaluate entire graph all in one go and trying to get some idea of which is your failure node. Now, because this analysis is being done for the entire test case, the key requirements become that this has to be infinite depth. That means that no matter how long the run is, you're able to extract this high-level analysis from the run. The second requirement is that because this analysis is being done for the duration of the test case, so the impact on the performance and impact on the throughput should not be there. That means that all of the analysis, system level analysis that we are trying to do, it has to be at speed. And if we are able to achieve these two requirements, then it can also be enabled in regression. That essentially means that you have reduced one iteration to debug the problem, because in your regression, when the test case fails, you already have the higher level analysis and the data dump generated for you to do second level analysis. Second challenge that we laid out is that we need to have a solution for deterministic bug reproduction when we are operating in high throughput emulation. So here the key requirement is that we need to find a solution that can reproduce the failure deterministically in every subsequent run. And the goal here is, or the requirement again is, that we don't ever want to miss a transient failure, which may be a bug because of the specific timing of the test bench. Third requirement, or the third challenge that we described, is scalability of waveform-based debug for billion gate SoC designs. And here, what we really need is a next generation tools that can process large waveform through native integration of your debugger. So now that we have understood the three challenges and the requirements to resolve those challenges, let's look at what solutions ZeBu Exascale Debug has to overcome those challenges. And the three things that I'm going to talk in this section are system level abstraction, deterministic replay, and the scalability of the waveform. So let's start off with system level abstraction debug with ZeBu. As we laid out earlier, here the goal is that we want to do high level analysis of entire design over entire run period of billion cycles or more. So in terms of technologies and the capabilities, ZeBu actually offers multiple streaming capabilities to abstract system level data. So you have the abstract logs, those could be monitors or checkers of all the key interfaces of your design. We have the ability to dump all the key signals of the design. We also support language features like assertions, system tasks, etc. Now, what is what stands out really about all of these solutions is that this is all happening at speed. So when we enable these technologies, it doesn't slow down your run, and it comes at zero performance impact. The other thing that we offer is that these solutions are infinite depth. So it really doesn't matter how long your test case is. You can enable from time zero and let your regression run for hours or days, and we would still produce the data covering the entire run. Now, also I talked about the streaming capability. What it means is that emulation clock doesn't stop. We are constantly streaming data out of the emulator, and which means that there is no throughput impact. So now, once you've dumped all of this system level data in the regression at speed, the next step is how do I use this data to find my window of interest. And so this is where you're doing offline analysis of the data. So you're using your checkers for a coarse grain search, and then you're using your monitors and key signal waveforms for refining the window. And that allows you to go from billions of cycles of original runtime where the failure happened to a few million cycles where you have kind of located the problem that it is within these million cycles, and this allows you to go in-depth analysis and focus that small segment. And the beauty of this solution is that, as you can see, this is all single pass. You enabled all the streaming capabilities in regression. You did the offline analysis, and through a regression run itself, you have, using ZeBu system-level debug, you have found your failure window in single pass. So now let's talk about the second challenge that we had laid out, which is deterministic error reproduction, and let's see how ZeBu debug solves this problem. So there are a couple of technologies that I'm going to talk about, and the first one is ZeBu record and replay. This applies to the test bench, and the goal here is that we want to eliminate any non-determinism that is caused by the test bench by exactly replaying the test bench activity in subsequent runs as it happened in the main run when the problem was observed. The second technology is ZeBu save and restore. This is applicable to the design, and the benefit is that it eliminates the need to restart from time zero. So when you hit an issue through ZeBu save and restore, you can start from closer to the failure point and save the time by not running from time zero. Now, both of these technologies actually work hand in hand. So when you're doing the main run, you're going to do the stimuli recording on the test bench and DUT interface. So as the test case is progressing and as the time is moving forward, the test bench activity on the DUT interface is recorded, and that is being shown as number 0, number n, number m, etc. in this picture here. Now, when the second thing that we are doing while doing these runs is that we are also periodically storing entire DUT state in a database. So let's say that user defined an interval, and we've got 3 save states during the run before my test case finishes. And let's say this is the run when we saw the failure, and this failure happens to be somewhere between second save state and third save state. Now, when you want to do the replay, as you can see, we are, number one, we are not starting from time zero. We are actually starting from closer to the failure. So we are restoring the DUT at time n, and rather than using test bench to drive the DUT, we are actually using the recorded stimuli, and we are replaying those to drive the DUT. So by doing this, now we can deterministically reproduce the timing as it happened in the main run, and that helps us reproduce the problem consistently. And once you have seen the problem, you can focus your debug around the failure point and find the root cause. So essentially, by applying record, replay, and save and restore technologies, ZeBu is able to deterministically reproduce your problem. So let's talk about the third challenge that we laid out, that the waveform engines need to scale for the exascale debug. And here, what I'm going to present is ZeBu solution that can produce 10x faster expansion and load. And we are actually achieving it through really next generation tools to address the exascale debug complexity. So typically with, as we were describing earlier, that from the emulator, you're dumping raw data which is of some essential signals, combinatorial signals, and then you're doing the expansion into the full visibility waveform. Now, what ZeBu offers is, number one, it offers a very high bandwidth interface. So the data that is coming out of emulator, and with bigger designs, the data can be large, so that data can stream out really fast. Second thing that we offer are expansion engines. So we have high performance parallel expansion, or you also have the option of high performance and efficient interactive expansion, which then produces full visibility waveform through native integration into Verdi. Now let's look at some of the numbers. So this interface coming out of the emulator is high bandwidth. We support up to 2 terabytes per second. Some numbers for the parallel expansion. So here we have a 750 million gate design, and we are trying to evaluate a waveform of 1 million cycles, and the complete expansion time is less than 10 minutes. So at the end of this time, you get every node of your design expanded to its value, and then you can see that in Verdi. The second path you can take is really interactive expansion. So here results are actually impressive, that 2.5 billion gate design, we are trying to expand a waveform of 500k cycles, and then each signal drag and drop is less than 1 second. So the advantage of this methodology is that as soon as you have your raw data dumped out of emulator, you can, through the native Verdi integration and interactive debug, you can immediately load it in Verdi and do this interactive drag and drop to start seeing your waveform right away. The other key aspects that we built into this solution is that Verdi has a new native ZeBu format, which really improves the expansion time and the load time into Verdi. So as you can see that ZeBu offers a scalable solution that can address complex billion gate SoC waveform level debug. So now that we have discussed the three challenges, requirements, and how ZeBu is addressing those three requirements, let's see how the big picture looks like. How all of these three solutions come together to form a consistent flow for debug. So the very first thing you're doing is that you're running your billion cycle workloads at megahertz speed. Now, during this period, while the run is going on, you're doing many things. You're streaming out system level data, which is at speed and which is in finite depth. You are also doing recording of your test bench stimuli, and then you're doing DOT save at periodic interval. Now, based on the failure that has happened, you're going to analyze the system level data, and based on your analysis, you're going to pick a particular DOT state from where you want to restore, and correspondingly, you're going to decide which test bench stimuli need to be applied. So you're going to restore the DOT, and rather than driving the test bench, you're going to use the test bench stimuli to replay the design for deterministic reproduction of the bug. Now comes the waveform level debug. So now that you are in the failure window, you can really do full visibility waveform and use interactive Verdi and native Verdi integration for the debug and root cause the problem. Let's look at some of the customer success stories using ZeBu Exascale Debug. The first case study I'm going to talk about is AMD. So they have a really complex design, and the environment that is this is for their graphics design, which is several billion gates. And if you look at the environment, it is built into it has several interfaces. A lot of components are connected through virtual platforms. And then they are doing the OS boot driver development, and they are running some applications, and the workloads are really billion plus gate designs. So in this slide, they are talking about how using ZeBu Debug, they are able to deterministically debug a problem in an environment which is originally non-deterministic. So they are actually using the save and restore and record and replay technology to reproduce the problem deterministically. And this slide talks about their overall debug methodology, where they are doing the system level analysis through some fast waveforms that are dumped for the entire duration, and then they are able to, based on the bug, they are able to get, rather than starting from time 0, they are restarting from close to the failure point, and then they are doing the debug and finding the root cause. The second case study I want to bring up is a networking company where we helped them debug a really complex problem. So this was also a non-deterministic failure, which would happen from anywhere from 1 to 7 days. It was a long-running benchmark test, and on a multi-core design, and they asked our help to find the root cause. So let's quickly review the flow that we put in place. So we enabled the record, replay, and save and restore technology, so that when the failure happens, we need not start from time 0. So these are the save states that are shown here. Now, also along with that, we enabled dump of the program counter for all of the cores, and this was being done at speed, infinite depth, and no impact on throughput. Now, after this, based on the analysis, we first found the window of failure. Within that window of failure, we enabled further debug utilities to find the even smaller window of failure. And within that window, then we did the full waveform capture and found the problem. So in this particular case, when we were debugging the problem, the non-deterministic run actually crashed in about 2.5 days. And it took us close to 4 hours to find the root cause. And this was possible because we need not start from time 0. We need not do multiple iterations. And through effective application of ZeBu Debug, we were able to get to 4 hours type of time to root cause. The last case study I want to talk about is IP provider, where they are using the streaming capabilities to effectively narrow down the failure of window of failure. So from the billion of cycles of runs, they have enabled some of the system logs which are low impact. So these are running for the entire duration, and with that analysis, they are able to go from billions of cycles to millions of cycles. And then in the second iteration, they enable some additional trackers and monitors, including some of the key interface waveforms, etc., to further narrow down the window from millions of cycles to even a smaller window, million or less cycle. And when they get to this window, they are able to do full visibility waveform dump of million cycles, or in some cases they even do multi-million cycle dump, and finally use native ZeBu Verdi integration and the next generation waveform scalability solutions to root cause the problem. So as you can see here, this shows a very effective use of ZeBu system level debug to reduce time to root cause by reducing number of iterations. So let's quickly summarize the webinar and ZeBu Exascale Debug. So we talked about increasing scope of emulation and increasing scope of complexity from a design that is million of gates running a smaller workload that are million of cycles to billion of gate design, SoC designs running billion of cycles. To address this kind of debug complexity, we talked about higher level of debug abstraction, going from waveform level to system level to application level. And then we also talked about how ZeBu Exascale Debug provides a framework to solve the exascale debug complexity problems. So this is really the fastest way to root cause complex billion gate SoCs with billion cycle workloads. So thank you everyone for listening in, and I'll jump right into some of the questions that have been sent. So I'll read out the questions and then I'll try to answer. So the first question I have here is, it seems tedious for me that with system level debug, I would always need to run my emulator again to dump the debug data. While with my current method, I can dump 1 million data points immediately after my trigger fires. So thank you. That's an excellent question, and you're right that you can have some waveform immediately at the failure point with your current method. However, you need to consider that in many exascale problem cases, the actual bug will likely not happen within that window. So you will have to rerun to find another debug window. You will also, in most cases, need to rerun from the beginning. So unless you're working on the bugs that happen quickly and close to the failure observation point, your overall debug time with only waveform-based debug is going to be much longer. Okay, let me take another question. And the question is, it appears that you believe that waveform level debug is less important than system level debug. Can you comment some more? So actually, excellent waveform level debug technology is critical and essential for exascale design debug. Once you've dumped the relevant time window, you need the fastest waveform expansion with native integration into your waveform tools. However, what I have explained earlier is that with only waveform level debug, your search algorithm for the bug is not efficient. Remember the depth first search example I gave. If you have to debug many waveform windows to narrow down the problem, you will spend much more time overall compared to starting with system level debug. Okay, so I think I have time for one last question, and the question is, I have not run into non-determinism with my emulation method, even though I'm not using a replay approach. Why is that? Thank you. That's a very good question. So actually, If you recall, I covered two potential reasons for this earlier. Number one, it may be pure luck, which is obviously not a good plan to meet your project schedule. Or the second reason that I covered is that in case of low throughput emulation, what you're doing is that you're using a start and stop method for the emulator, and you're decoupling the test bench from the DUT execution. So what will happen is that with this approach, while you are deterministic, but you're going to leave a lot of performance on the table. So the amount of cycles you can verify with this method is going to be severely limited. And cutting down billions of cycles from your emulation run is not a real option when you want to verify the SoC with actual software workloads. So thank you all. Thanks for joining and listening into the webinar, and have a good rest of the day. Thank you.